Hello, everyone. Have you ever wondered why the selection of mates is not random? This pattern isn't just a coincidence. It's called assortative mating, and it plays a fascinating role in shaping the genetics of populations. It's also connected to other important genetic concepts like inbreeding, linkage disequilibrium, and population structure. I know these are big terms, but don't worry, I am going to explain what those terms mean. Assortative mating is a type of non-random mating where individuals are more likely to pair up with others who share certain characteristics. This could be based on traits such as height, intelligence, or even hobbies. There are two types of assortative mating: positive and negative. Positive assortative mating occurs when individuals prefer partners who are similar to themselves. For example, people with a yellow skin tone might marry others with the same skin tone. On the other hand, negative assortative mating occurs when individuals prefer partners who are different from themselves, such as when people with different skin tones pair up, leading to greater genetic diversity. Let's dive into Bob and Lucy's story to understand more about positive assortative mating. Meet Bob. He's been looking for that special someone for a while now, but finding a match hasn't been easy. You see, in Bob's society, there's something called Hardy-Weinberg equilibrium, which is basically a balance in how traits are spread out. There are 5 rules in his society. No mutations. New genetic variations or mutations must not occur, so the gene pool remains stable. Random mating. Individuals in the population must mate completely at random with no preference for similar traits. No natural selection. All traits must be equally likely to survive and reproduce, so one genotype doesn't become more common than another. Large population size. The population must be large to minimize random changes in gene frequencies. No gene flow. New genes from other populations shouldn't mix in, meaning no new individuals enter or leave. Let's say for Bob's society, the yellow color is recessive and represented by little g. Thus, Bob's genotype is little g, little g. Why? Well, because Bob, like us, is a diploid organism, meaning he has 2 copies of each gene, one from his mom and one from his dad. Let's take a look at Bob's parents' genotypes to understand more about Hardy-Weinberg equilibrium. Bob's dad is little g, and Bob's mom is big G, little g. They didn't pick each other because of their genes. Instead, they met and paired up randomly without considering things like color or traits. In Bob's society, it's not about choosing a mate based on similarities or differences in traits. They are just as likely to pair up with anyone in this particular population. So Bob's parents are a random match. Hardy-Weinberg equilibrium has mathematical representations. It consists of 2 equations that describe how allele and genotype frequencies are distributed in a population. Let's explore the math. First one is p plus q equals 1, which represents the frequency of alleles in a population, with p equal to the frequency of the dominant allele and q equal to the frequency of the recessive allele. And second one is p squared plus 2pq plus q squared equal 1, which is used to calculate diploid genotype frequencies in a population. The value of p and q is the frequency of homozygous, and value of 2pq is the frequency of heterozygote. Let's assume in Bob's society, the frequency of big G allele is 0.4, the frequency of little g allele is 0.6, which makes the frequency of the p squared genotype 0.16, the frequency of 2pq is 0.48, and q squared is 0.36, which adds up to 1. This means Bob's society is in Hardy-Weinberg equilibrium. However, Bob has always wanted someone who is similar to him, which will potentially break the rule of random mating. One day, everything changed. At work, Bob noticed Lucy, who was just like him. Same color, same interests, same warmth, and even the same genotype, little g, little g. They quickly realized they had a lot in common, which brought them together. This is called positive assortative mating. Bob and Lucy decided to leave their village to start a new adventure together. They settled on a remote island, which broke some important Hardy-Weinberg conditions, such as large population size and random mating. This situation led to something called the founder effect. The founder effect occurs when a small group of individuals establishes a new population. Since this smaller group doesn't represent the full genetic diversity of the original population, certain traits, like Bob and Lucy's yellow skin and little g genotype, can become more common or even fixed in future generations due to chance. The island was home to a small, isolated group of people, and due to the limited population size, many of them began to practice inbreeding. With such a small gene pool, individuals were more likely to mate with close relatives, leading to a decrease in genetic diversity. Shortly after, Bob and Lucy had children who looked exactly like them, sharing the same yellow skin tones. They were happy about this because both were fascinated by the unique traits they carried. One day, Bob was reading about Queen Victoria and learned that historically, many royal families married close relatives such as siblings, cousins, or other close family members to maintain power and wealth, a practice known as inbreeding. This practice, however, can lead to genetic issues because inbreeding increases the chances that offspring inherit identical alleles from both parents. The British royal family is known for this, with Queen Victoria passing on the hemophilia gene through her descendants, which affected many royal families in Europe. The concentration of recessive genetic disorders due to inbreeding can lead to serious health problems, such as physical disabilities, decreased life expectancy, and changes in population structure. Instantly, Bob started to worry about his descendants. As you all know, Bob and Lucy started their family on a remote island. Bob wants to understand all the potential consequences before making any major decisions. To learn more, Bob applied a formula, believing that math always reveals the truth. To calculate the percentage change, Bob needs a constant called the inbreeding coefficient, indicated by Fi. There are 3 formulas to find the percentage change for inbreeding. In this case, we will focus on how the frequency of the recessive little h genotype changes after inbreeding between siblings, which can lead to a genetic disorder. Let's assume P is 0.7 and Q is 0.3 for this calculation. If 2 siblings in a family marry, inbreeding increases the frequency of little h alleles by 25%. This makes Q squared plus P times Q times F rise, increasing the frequency of little h from 9% to 14.25% in the population. This change shows that inbreeding raises the frequency of genetic disorders by 5.25% in the population. Bob also revealed that inbreeding increases homozygote frequency and decreases heterozygote frequency. Additionally, linked genes can create a phenomenon known as linkage disequilibrium, which may contribute to changes in population structure. Linked genes are genes that are located close to each other on the same chromosome, which makes them likely to be inherited together during meiosis. Because linked genes do not easily separate through recombination, they are more likely to be inherited together rather than independently, more often than would be expected by chance. This non-random association of alleles at different loci is what is called linkage disequilibrium. If a royal family member has a particular trait linked to a genetic disorder, their offspring are more likely to inherit both traits together, increasing the risk of genetic diseases. The formula for linkage disequilibrium is D equals product of P1 and P4 minus product of P2 and P3. Plugging in the values, we find that D equals 0.07, indicating that there is linkage disequilibrium. This means that alleles big G and big H, and similarly little g and little h, are found together more often than would be expected if the loci were inherited randomly based on the allele frequencies in a particular population. In other words, there is a non-random association between these alleles, indicating some level of genetic linkage between the loci. If the D value is not equal to 0, it can be either positive or negative, indicating that the allele combination is in linkage disequilibrium. A D value of 0 suggests independent assortment, meaning the alleles are inherited randomly within the population. Imagine this trend continuing over generations in Bob's new population, which might develop a different trait from the neighboring population that doesn't practice assortative mating. Over time, this can lead to less interbreeding, more inbreeding. In an extreme scenario, these genetic differences could become so pronounced that the two groups might eventually be unable to interbreed. Now you might be wondering, how do scientists measure the genetic differences between populations? Well, they use a statistic called FST, which stands for the fixation statistic, which has some relation to Fi that was mentioned earlier. Scientists measure the extent of genetic divergence between groups using the FST value. The FST value compares genetic variability within and between populations. FST values range from 0 to 1, where 0 is the minimum and 1 is the maximum. An FST value of 0 indicating that the populations are interbreeding freely. An FST value of 1 indicates complete genetic differentiation between populations, meaning they are genetically unique. For example, in Bob's original community, frequent mating among members led to a well-mixed gene pool and a higher level of heterozygosity, resulting in low FST values around 10%. These hypothetical numbers show high genetic similarity within the population, which indicates high genetic similarity. Assortative mating, however, does not significantly influence population genetics if the population is large. On the island where Bob moved, the FST value between Bob and Lucy's group and the small isolated population already residing there is 1, indicating that they are completely genetically different from one another. This means there was no interbreeding between these two groups. As Bob moves to a new area and interacts less with his old community, gene flow between the two populations decreases. This reduction in gene flow leads to greater genetic differentiation and, over time, increases homozygosity. As gene flow decreases, the FST values between Bob's original community and the new population gradually increase, reaching 0.4 relative to the old community. This indicates a decline in interbreeding, leading to greater genetic divergence between the two populations over time. Apart from humans, positive assortative mating can also be observed among animals, such as peacocks. Peacocks select mates based on the color of their feathers. Therefore, positive assortative mating can decrease genetic diversity because similar individuals are likely to pass down the same genes. With less diversity, a population might struggle to adapt if the environment changes. Additionally, there's an increased risk of genetic disorders when similar genes pair up, particularly if they carry harmful recessive alleles. And over time, this preference for similarity can even lead to inbreeding within small or isolated populations, potentially reducing the overall fitness and health of future generations. However, positive assortative mating can help preserve certain traits in a population, like height, eye color, or skin color. This preservation can be beneficial if those traits offer advantages, like adapting well to the environment. Now, let's talk about negative assortative mating. This type of mating occurs when individuals prefer partners who are genetically different in certain traits, and it's less common than positive assortative mating. But why would organisms choose mates that differ from themselves? The answer lies in genetic diversity. When two individuals with different traits, like immune system genes, pair up, their offspring inherit a mix of both. This mixing can strengthen the immune system, as diversity in immune system genes enhances the ability to recognize a wider range of pathogens, making the next generation better at fighting off diseases. Studies suggest that in humans, people may be more attracted to the natural scent of others with different MHC genes. The major histocompatibility complex, MHC, is a group of genes that encodes proteins involved in the immune system. A well-known example of negative assortative mating outside of humans is seen in the white-throated sparrow, a bird with two color morphs, tan-striped and white-striped. These birds almost always pair with a partner of the opposite color. Scientists have found that this isn't random. Tan-striped and white-striped sparrows exhibit different behaviors. For instance, tan-striped males are more nurturing, while white-striped males are more aggressive. When they pair with an opposite type, it balances the parenting roles and increases genetic variation in the population. But here's the catch. Negative assortative mating doesn't just make things interesting for the sparrows, it also helps maintain genetic diversity across generations. By avoiding mates who are too similar, populations can prevent inbreeding and maintain a healthy level of genetic variation. This has significant consequences for the survival and adaptability of the species. Negative assortative mating is an evolutionary strategy. By promoting genetic diversity, it helps populations adapt, survive, and thrive in changing environments. This mating type increases heterozygosity by pairing individuals with different alleles, which reduces homozygosity across the population. Higher heterozygosity can lower linkage disequilibrium. By breaking up alleles combinations, as more alleles yields more haplotype options, and so the bias for certain combinations is more likely to be disrupted with each recombination event. Additionally, negative assortative mating can reduce genetic differentiation between subpopulations, resulting in a lower fixation statistic, FST. By promoting genetic diversity and reducing the frequency of similar allele pairing, this type of mating reduces inbreeding, which lowers the inbreeding coefficient, Fi. However, it may slow the fixation of advantageous alleles, potentially slowing adaptation in environments where those traits are beneficial. Both positive and negative assortative mating have distinct pros and cons. While Hardy-Weinberg predicts genetic stability, factors like assortative mating, genetic isolation, rising FST values, and inbreeding reveal how this balance can shift in fascinating and sometimes challenging ways. After learning the negative consequences of assortative mating, Bob and Lucy started to worry about the future of their descendants and shared their concerns with their families and friends. Luckily, they had great friends who understood the importance of genetic diversity, and they agreed to join Bob and Lucy on the island. Soon, they arrived with their families, infusing the community with new energy and genetic diversity. With their arrival, Bob and Lucy's island began to flourish, growing vibrant and diverse. Thanks for watching. If you enjoyed this video, please give it a thumbs up and hit that subscribe button to support the channel. Don't forget to turn on notifications so you don't miss any of our future videos on genetics, evolution, and more. Stay tuned for more fascinating insights and drop a comment below if you have any questions or topics you'd like us to cover next. See you in the next one.